Our today's topic is inverse Z transform. What is inverse Z transform? In the starting only I told you, and by now you must have known what are transforms and what are inverse transforms. We had seen that if we have a discrete function or discrete signal xn, we take a Z transform of this function so that we get a function. This is x, so we will get xz. This is Z transform. So the inverse of this is inverse Z transform. That is, we will get this original signal if what we do is inverse of this xz. Simple. This is the way we find inverse Z transform. Now, how we find Z transform? That is an inverse Z transform. That is important. There are several methods. There are several techniques. First is power series method. Second is by partial fraction method. If you have, you must have studied Laplace transform by now. So you have seen by using partial fraction method, we get inverse Laplace transform. Similarly, here also we have segregate functions by partial fraction method and get the inverse Z transform. Then there is a residue method also. So let's see all of them one by one. First is power series method. What is this method? Here we do two things. First is, I shouldn't say first. Here we take functions of z which cannot be segregated using partial fraction method, or we have difficulty in segregating using partial fraction method. So we take this. Here we have two types of methods. We have a function in numerator versus denominator type functions which cannot be segregated into partial fractions. Here what we do, we divide it. We divide numerator by the denominator and we take it as a series. I'll do examples and we'll understand this. And second is, we have several functions. For example, log 1 plus x. We expand it, or 1 plus z to the power minus n. So you should know these expansions. Maclaurin series, any series, you should know these, the expansion using any series. First 3-4 terms in that expansion you should learn it by heart. We'll use it. So let's start with this first and then we'll see the second one. Okay, so let's see this example. I told you this is numerator by denominator. It's not possible to segregate it into partial fractions. So what we'll do, we'll divide it. See how. You know how to do division. It is z square plus 2z plus 1. So what will be the first term with which we'll multiply this and get this? We have to get z. So if we multiply it by z inverse, 1 by z inverse, what we'll get? We'll get z plus 2 plus z minus, sorry, z inverse. This is what we'll get. So minus this, what do we get? We get z minus z gone, so it is minus 2 plus z inverse. So this means this is z inverse minus 2 plus z inverse by z square plus 2z plus 1. Okay, now let's take the second one, again dividing by this. So to get this, what we need, see, this is minus 2, so we'll have to take minus, so that this minus this is actually it cancels this. So we have effectively minus 2. So what we'll do, if we multiply this function by 2z minus 2 and minus, what you will get? You will get minus 2 here, then minus 2 into 2, 4, and z inverse, then minus 2z inverse, to the power 2. Okay, so this minus this is minus 2 plus 2 gone, minus z inverse plus z inverse. So this will be 3z inverse and this is plus 2z minus 2. Okay, so now the next expansion is z inverse minus 2z inverse, sorry, not inverse, to the power minus 2, and then this is plus, so plus 3z inverse plus 2z minus 2 by z square plus 2z plus 1. Okay, this is not very clear from these two terms. So let's do one more term. Now we have to get 3z inverse. How to get 3z inverse? If we multiply this by 3z to the power minus 3, what we'll get? We'll get 3z inverse. Okay, so we get 3z inverse. Here we'll get 3 into 2, 6, z minus 2. Okay, and then we'll get into this, that is plus 3z minus 3. So this minus this gone, this minus this, so we'll get 4z minus 2 and then minus 3z minus 3. So now our expansion is z inverse minus 2z minus 2 plus 3z minus 3, again minus, we have 4z minus 2 plus 3z minus 3 by z square plus 2z plus 1. So now we have understanding, it is 1, this is minus 2, then plus 3, then again we'll have minus 4 and so on. So how can we write this equation? We can write it like this. This is n equal to 0 to infinity. The first term is positive. Okay, so what we'll do, see, if we take minus 1 to the power n, no, if we take minus n, this will be minus, so we'll take n minus 1. Okay, now this is 1, 2, 3, so n, and then we have z minus n. Now let's see, we put n equal to 0, this is 0, so first term is 0, n equal to 1, it is 1 minus 1, 0, so minus 1 to the power 0 is 1, so 1 z minus 1, so first term we get n equal to 2, this will be 2 minus 1, so this will be minus, so this is minus n 2 z minus 2. So this is our sequence. So from here what we get is our xn is, you know the definition, xn is basically this is for transform. So what we get is minus 1 to the power n minus 1 n. This is your sequence. This is the discrete signal of the function. Okay. So we'll see now by expansion power series method. There are several expansions that you should learn by heart. For example, log 1 plus x, it is x minus x square by 2 plus x cube by 3 minus x4 by 4 and so on. 1 plus x to the power minus n, it is 1 minus n x by 1, n into n plus 1 by 1 to 2x square minus so on, this way. E to the power x, it is this, okay. So in place of x, if you have minus x, that is you have log 1 minus x, what you have to do is you have to put minus x in place of x, that is it will be minus x plus x square by 2 minus x cube by 3 and so on. 1 minus x, so it will be 1 plus nx by 1, this is plus, so all the terms will be plus. Similarly, you put e to the power minus x, you have to just put the values of minus x. So you should learn it by heart, this is required. Now let's see an example on this. Later on we will see on this also, but first of all let's see on the log 1 plus x, remember it is x minus x square by 2 plus x cube by 3 minus x4 by 4. So let's see our first example. So our example is xz is log of z by 1 plus z. We have to find xn, inverse z transform. So we can write it like this also, minus log 1 plus z by z, this you know about log, and this can be written as minus log of 1 plus z inverse. Now this is in the form log 1 plus x, so we can write it as minus, this is x is here, z inverse, so it will be z inverse, then second term is negative, so minus by 2 plus 3. What I have done, I have just expanded it. Okay, so now what we can do is take this negative here, so this will be minus z inverse plus z minus 2 by 2 minus 3 plus z and so on. What can be the term? See, if we take minus 1 to the power n, so for 1 this is okay, for 2 we need this by this, that is 1 by n. So if you take 1, n equal to not 0, n equal to 1, what you will get? You will get, see, for 1 this is minus, this is 1 1, so you will get minus z inverse. For 2 you will get, this will be positive, and then z minus 2 by 2. So this is good. But at what about the value of this expression at n equal to 0? See, this is in the denominator, so n equal to 0 will not get any result. So this has this particular sequence. This means that this sequence is not defined at n equal to 0, otherwise it is this. So our answer will be, so xn is the sequences, it is 0, sorry, not 0, it is minus 1 to the power n z, sorry, not z, 1 by n for n not equal to 0. So at n equal to 0 it is not defined, otherwise it is this. Okay. And when you can understand one thing more, in this expression we don't have any value for z to the power minus 0, that is for n equal to 0, that is this value is actually 0, first value. So this is this for n not equal to 0, and this is 0 for n equal to 0. So this is the sequence. Okay. Now let's say in this example we'll solve it by partial fraction method. When you have to take inverse z transform using partial fraction method, what you need to do is you take xz by z, and then we'll see what is xz. When you take xz by z, you need one z, you have to remove one z, so this will now be 2z this. Okay. Why? I tell you why. See, you know that z transform of a to the power n is z by z minus a. Now you understand, if we have certain function as z by this, we can take the inverse to the as a to the power n. So if you have taken this, when we will multiply, we will get z by plus 2. Now let's see what is, how can we represent it in partial fraction? You know how we do this? We do this like this: a by z plus 2, let this be this. So our problem is to find a and b. What this will be? It will be a z minus 4a plus b z plus 2b, that is a minus a plus b z. Then we have minus 4a plus 2b. Okay. So a plus b is 2, and minus 4a plus 2b minus 4a plus 2b is 3. This is what we get. So let's multiply 2a 2b, this is 4. Okay. Now let's minus this minus this. So 2a minus 4a will be 6a. This minus this is gone. 4 minus 3, 1. So a is 1 by 6. So here we get a, that is 1 by 6. And we have seen a plus b is, I'm writing it here, a plus b is 2. Okay. So b is 2 minus 1 by 6. This will be 13 by, no, not 6, 12. 12 minus 1, 11, not 13. So this is 11 by 6. Okay. So this term is 11 by 6. So your function is actually, now you know your xz is 1 by 6 of z by z plus 2 plus 11 by 6 of z by z minus 4. Now you understand why we took xz by z. Now our function is like this. So what will be xn? See, compare it with this. This is minus 2. Your a is minus 2. So it will be 1 by 6 minus 2 to the power n. This is the first term. Second term is 11 by 6. This is 4. 4 to the power n. So this is your answer. Okay. Now we have understood. Basically, we have understood how to take inverse Z transform. I haven't given several examples to make you very comfortable, because that is fundamentally mathematical understanding only. I am now switching to difference equations. How we solve difference equations using Z transform. We'll have mathematical foundation for Z transform, and then what we'll do, we'll get into signals, and we'll see several signals and how to analyze the signals. So there we'll be doing a lot of mathematics on Z. So we have, let's build our mathematical foundation and then we'll get into signals. Now this is the difference equation. Now let me give you a recap. We have seen that if un corresponds to uz, that is the z transform of this is this. This is another notation, and more frequently in signals you will find this notation, and this is better also. Why? Because u is also always not always, often confused with unit step function. So better to use this function, but you'll find both types of notations being used. So if this is the case, you have seen un minus k is actually z to the power minus k uz, or in terms of xn we can write x n minus k, this side shifting to n minus k this side. So this is z minus k xz. In this, both are same. I'm making you familiar with these notations. Okay, so you should keep this in mind. Then what about un plus 1? If you remember, z transform of un plus 1, this is what? It is z uz minus u0. Then z of un plus 2, z square uz minus u0 minus u1 z inverse. These things we have discussed in the first class only, but you should remember, because now we will be solving differential equation. So if we have to take z transform of this, we have to know this. So I'm just giving you a recap. This was z cube uz minus u0 u1 z inverse u2 z minus 2 and so on. So this is expansion. Okay, in terms of, if you want to know how to see this in this form, then we have, see, z transform of x n plus 1, we'll write it like this. This is given as z into xz minus x0, or not subscript, we'll use it like this. So this is in this form. Same thing, if you have to write it here, these two also, let's see, z transform of xn plus 2, like we'll be doing it here. It is z square xz x0. Then what we have to take? First u0 u1. So x1 z inverse. This is this thing. Why I'm telling you? Because you will be, you'll get confused if you do not use these frequently. Sometimes use for un, sometimes use for xn. Otherwise, you'll get confused. So n plus 3. Let's see what it will be. It will be z cube xz minus x0 minus x1 z inverse minus x2 z minus 2. Okay, so these are simply different notations. So let's see. So here it should not be this, this should be x0 is 0 and x1 is 1. So let's see, let's take z transform, and this is a to the power n, and you know that z transform of a to the power n is z by z minus a. So here it will be z by z minus 3. So taking z transform on both sides, this will be, I just told you, z square xz minus x0 minus x1 z inverse. This will be 4z xz minus x0. Okay, this is simply, writing it here, it is simply 3xz. This is z by z minus 3. Okay, now x0 is 0, this is 0, this is 0, and x1 is 1. So what do we get? We get z square xz minus z inverse plus 4z xz. This is 0, then plus 3 xz. This is z by z minus 3. So what you get it? Let's say we take the coefficients of x. It is, here we have z square plus 4z plus 3 xz. Okay, here we have minus z, only minus z, so this side it will be plus z. So z by z minus 3 plus z. This is our equation. Let me rub this. See, z square plus 4z plus 3. We can write it as z plus 1 into z plus 3. This you know. We can write it as z plus 1 into z plus 3. Is there any benefit? Let's combine these two. This will be z plus z square minus 3z by z minus 3. So z this, so we can write it like this, 2z. Okay, so here what we get finally, xz is, this is z plus 1 into z plus 3. So we get z square minus 2z by z minus 3 into z plus 1 into z plus 3. So this is our function. So you know how to expand it or how to segregate it using partial fractions. So this will be a by z minus 3 plus b by z plus 1 plus c by z plus 3. Okay, you know how to find. We'll take this, equate them all, and finally find the value of a, b, c. So should I do it for you, or okay, let's do it. So here what we get z plus 1 into z plus 3, that is z square plus 4z plus 3 into a. Then b, z minus 3 into z plus 3, so z square minus 9 into b plus c. C will be, see, z plus 1 into z minus 3, that is z square minus 3z plus 2z. So it is z square minus 2z minus 3. Okay, z square minus 3z plus z. So minus 3z plus z minus 2z. So this is c. Let's put a together. This is, we have a plus b plus c into z square. Then we have 4z. So 4a, no z, here we have minus 2cz. Okay, and then what about this one? It is 3a minus 9b minus 3c. Okay, now if you equate, what you get a plus b equated with this. So a plus b plus c, what is the coefficient of z square? Here it is 1. Then 4a minus 2c, it is minus 2, and 3a minus 9b minus 3c, we don't have any such term, so this will be 0. So now you can equate this and find the value of ABC. To save time, I am writing it directly. So what you get is 3 by 8 z by z plus 1, then 1 by 24 z by z minus 3 minus 5 by 12 z by z plus 3. So this is the value that you will get for xz. And you know what will be the sequence? This will be 3 by 8 e to the power n, so this is minus 1 to the power n, plus 1 by 24, this is 3 to the power n, this is minus 5 by 12 minus 3 to the power n. So this is the sequence. So for this difference equation, the solution is xn is this. Okay, let's see another example. This is in a different notation. I have deliberately I'm using different notations so that you get familiar with all types of notation. So if you take z transform, what this will be? It will be z square yz minus y0 minus y1 z inverse. This is what you get from here. From here what you will get? You will get z yz y0. But you see, y0 and y1 is equal to 0. So these terms will vanish. So what you will get is simply z square for this. So you will get z square yz. Here you will get 6z yz. This is 9yz. And this is a to the power n. So z by z minus 2. Okay. So this you can combine, z square 6z plus 9 yz is equal to z by z minus 2. Now if you see this, what it is? It is z plus 3 square. So finally what you get is yz is z by z minus 2 into z plus 3 square. Okay, now you can expand it. How to take partial fraction, you know, I'm directly writing the values. This comes to 1 by 25. First is 1 by z minus 2, then minus 1 by z plus 3 minus 5 by z plus 3 square. This is the expansion. Now, you know about this, the inverse transform of this, you know inverse transform of this. This is, if you remember, z transform of n into a to the power n. This was what? It was az by z minus a square. Okay, so here we have minus 3. So if we put minus, sorry, I haven't given z. So if we put minus 3 here, so how can we put it? Minus minus plus, so we divide it by 3. So that we put minus 3 here. Okay, so now we can take our inverse transform. Your yn will be 1 by 25 of first term will be 2 to the power n. Second term will be minus 3 to the power n, and this term will be 5 by 3 minus 3, sorry, n into minus 3 to the power n. Okay. Okay, let's see another example. Here we have yn minus 1. Up till now we haven't used it. It is very simple. You know, for un minus 1 it is z inverse uz. Nothing else. Here this is un, unit step function. Remember, this is not un, the sequence. So take z transform. Here we'll get yz. Here yn minus 1. So it will be 1 by 4 z inverse. This is n minus 1. So z inverse yz. This is unit step function. So transform will be 1 plus 1 by 3. This is n minus 1. So z inverse 1. Okay, clear? So what we get is, see, here we'll get yz is 1 by 4z. So it is 4z plus 1, 4z plus 1 by 4. Yz 1 plus 4z by 4. Okay, and this is 1 by 3z. So 1 plus 3z by 3z. Clear? So what we get is z cancels. What do we get? We get yz as c, or we can write it as z plus 1 by 4. Similarly, this is z plus 1 by 3. So we can write it as z plus 1 by 3, z plus 1 by 4. So this is our yz. Now, in this, when we were discussing inverse z transform, I told you there are 3 methods. First method is power series method. Second method is partial fraction method, and third method is called inversion integral method. We'll solve this using that third method. Okay, let's see. So our this difference equation has given us the value of yz, the z domain function, which is, so from here we know yz is z plus 1 by 3 by z plus 1 by 4. Now let's see what is yn using inversion integral method. Now according to inversion integral method, un, that is un uz, un is given as 1 by 2 pi I is for complex number, closed contour, it is uz zn minus 1 dz. Okay, in a closed contour. This is actually the sum of residues of this uz into zn minus 1 inside this contour C at the, I am writing inside C at the poles of uz. What are poles and zeros? You know, here 0 is, we'll put the numerator equal to 0, that is z is equal to minus 1 by 3. So this is the 0 of this function. And what is the pole of this function? This one, denominator. So z, this was 4 not 3. So z equal to minus 1 by 4 is the pole of this function. So this can be written, if you want, we want to find the value of this. This can be given, this is actually equal to this sum of residues. We have only one pole, so we have only one value. If we had 2-3 poles, we would have taken sum of all. Since we have only one pole here, this is actually given like this. See, limit z tends to minus 1 by 4. This is our pole. We'll multiply this into uz, into zn minus 1. This is from this definition. You should learn this by heart. So what you get is limit z tending to 1 by 4. This will be uz into this. So this is simply z plus 1 by 3 into z n minus 1. Now let's put the value of z here. So z tends to minus 1 by 4. So this will be 1 by 3 minus 1 by 4. So this is 12, 4 minus 3. So 1 by 12. So what you will get is yn is, here you will get 1 by 12, and here z is minus 1 by 4. So minus 1 by 4 to the power n minus 1. So this is your sequence. Okay. So here we conclude our mathematical treatment of Z transform. Now onwards, what we'll do, we have the mathematical background, we have the mathematical fundamentals. We'll start analyzing signals by using Z transforms. Okay, and then during that discussion only, we'll see the relationship between Z transform and Fourier transform. Obviously, discrete Fourier transform, that is Fourier transform applied to the discrete signals, or in case of difference equations. So we'll see the relationship between Z transform and discrete Fourier transform, and we'll also then study what is how to solve equations using discrete Fourier transforms. So let's complete our mathematical background.